Well, this is my video for chapter 12, number 27 in the questions at the end of the chapter. Number 12, or question 27 is saying at 40 degrees Celsius, H2O2 aqueous will decompose according to the following reaction. 2H2O2 aqueous produces 2H2O plus O2 gas. And tells us our data down here at the bottom. Then for part A of the question, it's asking calculate the average rate of decomposition of H2O2 between 0 to 0.16 times 10 to the 4th seconds, and use this rate to calculate the average rate of production for O2 gas over the same time period. So for part A of the question, let me pull up my marker. Part A of the question is asking for our rate. So our rate, we know that equals to the change of our H2O2 all over the change of time. And almost forgot the negative sign, it's supposed to be negative next to it. So pulling in our numbers for this equation, we get the change or negative change over H2O2 to be 0.500 minus 1 over the change of time, which is 2.16 times 10 to the 4th minus 0. And by plugging in the calculator, we get the number 2.31 times 10 to the negative 5th mole liter second. Okay, and for that part, we get our rate for H2O2. And to get our rate for O2, we use our essentially the mole ratio. So we know that 2 H2O2 will make 2 H2O plus O2 gas. And using mole ratio on this one, we know our rate for H2O2 is 2.31 mole liter second. And for the mole ratio on this, for every 2 H2O2, we need 1 O2. So essentially, we're just dividing our rate by 2. So 2.31 divided by 2 is equal to, plugging in our calculator, we get 1.16 times 10 to the negative 5th mole liter second. Essentially, that's it for part B, or for part A. And for part B, it's the same, but it wants it for the time periods of 2.16 times 10 to the 4th seconds to 4.32 times 10 to the 4th seconds. So we use our same equation. Part B, rate is equal to the change in H2O2. We almost got the negative sign in front, but we need the negative there, and the change of time. So we know that our rate, or changing or plugging in our numbers, we get rate is equal to, let me pull up, it's going to be 0.250 minus 0.500. And for our time values, we get the numbers 4.32 times 10 to the 4th minus 2.16 times 10 to the 4th. Let me double check the numbers. 4.32, 2.16, 2.50. Okay. We get this. Then essentially plugging in our calculator, we get the rate is equal to 1.16 times 10 to the negative 5th mole liter second. Okay, and to find our rate for O2, it's essentially also the same. So we get, or essentially the same as we did in part A. So we know that for 2H2O2 is equal to, or it produces 2H2O and O2. And our mole ratio in this would be, or using our mole ratio, we know our rate is 1.16 times 10 to the negative fifth mole liter second. And using our mole ratio, we know that 1O2 produces 2H2O2. Essentially, we're also, again, we're going to divide by 2. 1.16 times 10 to the negative fifth divided by 2 is equal to, smacking it in our calculator, we get 5.80 times 10 to the negative 6 mole liter second. Okay, and that's it for both of that, or all the answers. We know our rate here for O2 and a rate for H2O2 for that time interval for part B. And also for part A, we got our answers up here, 2.31 for that time interval and 1.16 for that time interval. Hello, and this is my question, this is my video for question 45, chapter 12. Here, number 45 is showing the dimerization of butadiene, which is 2C4H6 gaseous to 2C8H12 gaseous. It was studied at 500K, and the following data were obtained. So we get our table here, our nice little table. Then what the question here is, assuming that rate is equal to the change of mole liter and the change of time, determine the form of the rate law. So we're trying to find our rate law here, and from our rate law we can get our integrated rate law, and it also wants our value for our rate constant, which is our K. So the first step we want to do here for this type of problem is we look at the table. Essentially, we can't use our usual rate laws that we usually do. So essentially, we gotta find values of it using our integrated rate laws. So using integrated rate laws, essentially we get another table. So we got our table for our mole liter, then we get our table for the natural log of our mole liter, then the table for our inverse mole liter. So we know that here, or we know through our magic calculus box and also in our cheat sheet, that the natural log of our mole liter is a first order rate, and our inverse mole liter is a second order. So we look at these values, we could either take the slope out of this, and whichever one has the most consistent slope out of all of them is what type of order it is. So we know that for mole liter, just by looking at the graph or by looking at this table, it's kind of off. And for our natural log, it seems pretty much the same, and our second order seems pretty linear too. But here we're gonna look at our graphs to determine how linear they are. So I have them down here. So our inverse of our mole liter is a pretty straight one. I'll say this one's pretty linear. Then we have our natural log one. It's almost linear in the beginning, but there's also that big, the not so linear of it. So this might be our second choice. Our first choice so far is our inverse function. Then our natural log one is kind of off. Then we look at our mole liter, which is also not so linear. So just by looking at our graphs, the most linear one is obviously our inverse one. So we know our inverse integrated rate law is, just by scrolling down, is a second order. So what we're trying to look for right now is the form of our rate law. So the form of our rate law is rate is equal to K times C4H6 squared, which comes from it being the inverse function from our integrated laws is the second order one. Then the second part of the question is the integrated rate law of it. So the integrated rate law from our magic calculus sheet, from our sheet that's already derived, we get that second order ones are 1, take the form of 1 over our moliter is equal to k times our time plus 1 over our moliter, or initial moliter. Then, just by plugging in our values, we get 1 C, let me double check, C4 H6 is equal to K times time plus our 1 over C4 H6 initial. So this is the form of our integrated rate law. So what it's asking here for the third part of the question is determine the value of K of this reaction. So we determine the value of this K just essentially by getting the slope of this graph. So first we're going to look at the our table here. So we're going to get from here, all the way to here and here. So our change in time and our change of moliter. So we're going to scroll over here to our right. So we get that. So let's do triangle, or our change. Sorry about that. Our change in moliter and our change in time are equal to our K. So by plugging in our values, we get 147.006 minus 62.50. Sorry, that doesn't look like a 5. Fix this. 62.50 over our change of time. So 6,210 minus 195. And by smacking this in our calculator, we get the numbers 147.06 minus 62.50 divided by 6,010 minus 195. We get that our slope is equal to 0.0141, which is essentially 1.41 times 10 to the negative 1. Oh, I'm sorry, negative 2. Negative 2. Then liter mole, or liter per mole second. And that is the value of K. And that's it for this question. Hello, and this is my question for number 53, chapter 12. And here it's asking the rate, or it's telling us the rate law of the decomposition of phosphine, pH 3, is rate equals negative change of in moliter over the change of time is equal to the constant K times our moliter, or in this case pH 3. Since it takes 120 seconds for one molarity of pH 3 to decrease to 0.250 m, how much time would it require for 2 m pH 3 to decrease to a concentration of 0.350 m? So essentially, here we are giving our rate order, which is here it tells us, which is just 1. This is just it's taking it to the power of 1, so we know that the rate order is 1. So we know the rate disappearance too. It also gives us it. And essentially, using our magic calculus box, because deriving it, honestly, it takes too long to do it, or it's too complicated. So we know that using our little cheat sheet, our little calculus box, we know that the ln of our AT over A naught is equal to the negative constant, or negative k, times t. So here, the first step to do is step 1, or no, step 1 is to write what we know. So we know that it takes 120 seconds to 1.00 m to go to 0.250 m. And what we're trying to look for is t for 2.00 m to go to 0.350 m. So the first step, or next step here, would be step 2. Plug in what we know. So essentially we're looking for k at this point, since we have everything to fill in on our equation from the first part right here to get our k. So we know that the ln, our concentration after time, would be, our AT would be 2.50 over our initial. So our A naught is here, A naught, and our AT. So our A naught will be 1.00 m, and m is equal to our negative k times time. So here, essentially, we're looking for our k. So our time here, let me fix this right here. So our time here is 120 seconds. 120 seconds. So doing our algebraic manipulation, we get k is equal to the ln, or natural log of 250 over 1, which is just 0.250, and over 120. So, smacking this in our calculator, it should spit out the number 0.0116 inverse seconds. So that's our value k. So after finding value k, we could find the time for our second part of our decomposition. So plugging in those values, we get ln is equal to our AT, which in this case would be 0.350 m over 2.00 m is equal to our negative k, which is 0.0116, times our time, what we're looking for. We're also going to algebraically manipulate this to t is equal to ln of 0.350 m over 2.0 m divided by negative 0.0116 inverse seconds. And smacking this in our calculator, we get that time is equal to 150.26 seconds, which is basically 150 seconds. And that's how we solve for t. Hello, and this is my video for chapter 12, number 66. Here, number 66, it says the reaction 2NO2 gas plus O2 gas combines to make 2NO2 gas, which exhibits the rate law K NO2 squared times O2. So here, it's asking which of the following mechanisms is consistent with the rate law. So here, we're going to write out all the rate laws for the slow steps, whichever one agrees with it should give us this rate on this rate up here, and it will agree with the rate law. So first, we're going to write the rate law for this first one, which is K times N O to the power of 1 times O2 to the power of 1, which just by looking at it, it doesn't equal to our rate law that's given. So this does not agree with this mechanism isn't consistent with the rate law. So we go on to the next one. So we look at the slow step on this one, which is K, or we're at the rate law K NO3 times NO to the power of 1. And both of them are just put to the power of 1 since the coefficients are just 1. And we look at it, so we look at this rate law. It's not equal to this one up here, so this one isn't consistent with it. So, and for this third step, or for this third one, we combine both of the slow ones. Or, in other words, we just use a bit of Hess's law, and we get, we use Hess's law, so these two cancel out. So we just get 2NO plus O2 produces N2O4. So, writing the rate law for this one, we get almost forgot the K, NO squared plus, or no, not plus, times O2 to the power of 1. And we look at our rate law, and we see that this one does confirm with our rate law. So the following mechanism, the one that that is consistent with the rate law that is given, is this one right here. Then we can also do this bottom one just to see what it gives us. So by doing the slow one, we just get N2O2K to the power of 1, and it doesn't agree with our rate law that's given up here. So essentially the one that agrees with it is the third one here, due to Hess's law and writing the rate law for it, which they're both essentially the same and agrees with the rate law. And this is it for the last question.